Welcome to this explainer. Today, we're going to demystify the invisible shields that are basically protecting your entire digital life. Every single time you use your banking app or buy a concert ticket online or book a flight, there's this incredibly complex, hidden layer of security working furiously in the background. We're talking about database transactions, the ACID principles, and concurrency. Let's get right into it. Okay, so here is our roadmap for today to understand exactly how databases keep our most important information safe and accurate. We'll kick things off with the magic of transactions, see how they pass the ACID test, explore the chaos of concurrency, learn about taking back control, and finally look at real-world reliability. Section 1. The magic of transactions and understanding the basic unit of database work. So to really grasp how our data stays secure, we first need to look at the absolute fundamental building block of all database operations. A transaction isn't just one isolated action. It's actually a sequence of operations chained together that absolutely must succeed as a single unit. If you've ever thought hitting pay was just one step, well, think again. It's a bundle of steps that have to act as one indivisible entity. And this is brilliantly illustrated by a simple bank transfer. Step 1, money is deducted from account A. Step 2, money is added to account B. In a database transaction, if step 1 happens but step 2 fails, say, because of a sudden network drop, the entire transaction must fail. The system literally reverses step 1 to ensure complete data accuracy. Because, let's be real, you definitely wouldn't want your money leaving your account and just vanishing into thin air. Moving on to Section 2, passing the ACID test, the unbreakable laws of the database. These are the core rules that govern every single transaction. The A in ACID stands for Atomicity. This rule dictates that either all operations happen successfully or none of them happen at all. Going back to our bank transfer example, if money is deducted from your account but not added to the recipient's, Atomicity ensures the entire transaction is canceled right there on the spot. It is strictly all or nothing. Next up is C for consistency. The rule here is that the database remains valid before and after the transaction. You can think of consistency as essentially the database's immune system. It guarantees that data never becomes incorrect or corrupted during the process. If a transaction tries to break any predefined database rules, consistency steps right in, halts the action, and maintains perfect data integrity. Then we have I, which stands for isolation. And what's really interesting here is how isolation protects you in multi-user systems. It lets thousands of actions happen parallel to yours, completely invisibly, by creating this sort of digital bubble around your specific transaction. So your bank transfer doesn't get tangled up with someone else paying their electricity bill at the exact same millisecond. And finally, D for durability. Once a transaction is completed, the data is permanently saved, even if the system crashes. Durability is basically your ultimate peace of mind. Once that transfer is done and you get that success message, it's permanently recorded. It is completely safe from sudden server failures or random power outages. These 4 rules, atomicity, consistency, isolation, and durability, are the true bedrock of digital trust. But what actually happens when digital traffic reaches rush hour? Section 3, the chaos of concurrency, when thousands of users attack. Concurrency just means multiple users or transactions are accessing the database at the exact same time. Imagine thousands of users trying to buy the exact same pair of limited edition sneakers on an e-commerce site at the exact same second. Suddenly, the system is flooded with simultaneous requests, all fighting for the exact same piece of data. It creates this massive, overwhelming digital stampede. Now, without specific controls in place, this massive concurrency leads to some serious data problems that could disrupt the entire system. We're talking about the dirty read, the lost update, and the uncommitted data problem. These are a database administrator's absolute worst nightmares, because it means the data is no longer reliable. Let's break down the real danger of these concurrency issues. In a lost update, 2 users update the same data simultaneously, and one of the updates just gets completely wiped out. Imagine you and your partner depositing money into a joint account at the exact same time, and only one deposit actually gets recorded. Yikes! Then there's the dirty read. Here, the system bases its next move on temporary, incorrect information that hasn't actually been finalized yet. It's kind of like a store selling you an item based on inventory numbers that are right in the middle of being changed by another system altogether. It just leads to absolute chaos. Section 4, taking back control and restoring order to the database. Look, we obviously can't have our databases acting like the Wild West. So to restore order, systems use 2 really common control techniques: locking and timestamping.
The system can freeze out other users temporarily with locking, meaning if someone is editing a specific record, the database locks it down tight and everyone else just has to wait in a queue. Or it can strictly organize everyone in line using timestamping. That's where every transaction gets a unique stamp, which forces the database to maintain a strict execution order based on exactly when the requests arrived.
All of these controls are really aiming for one main goal: serialization. Serialization acts as the final traffic cop here. It verifies that even in the heaviest digital rush hour, every single transaction executes safely without any conflicts. It guarantees that simultaneous events happen in a perfectly orderly sequence without ever crossing paths or corrupting the database. Section 5. Real-world reliability. Where we see this in action. We interact with these systems constantly. Banking systems and ATMs, railway reservation systems, online shopping platforms, and hospital management systems. From preventing double-booked train seats on a busy holiday weekend to managing critical hospital records where a lost update could literally be life-threatening, these concepts are exactly what keep our modern digital infrastructure from just collapsing under the weight of billions of daily requests.
I really hope this explainer gave you a newfound appreciation for